Hello everyone, welcome to Engineering Explained channel. In this session, I am going to explain the Bernoulli's equation. Here, I will take the Bernoulli's principle and from that, how the Bernoulli's equation will be derived. That I am going to explain. The Bernoulli's equation is applied for the different fluid flow through the pipe, and that I am going to take here. First, I will take the statement, the total mechanical energy. The total mechanical energy of the fluid flowing non-viscous fluid, that is does not have the viscosity. The viscosity is the resistance offered by the one layer of the fluid to the another adjacent layer of the fluid, and that resistance is not present in the fluid. That is called as a non-viscous fluid. In steady flow, the flow is steady, means the rate of flow of the fluid does not vary with respect to time. Incompressible, the fluid flow is not compressed, get compressed. Therefore, the density does not changes. That flow consists of pressure energy, kinetic energy, and potential energy. The flow of the fluid, the total mechanical energy, which is the sum of pressure energy, kinetic energy, and potential energy. Pressure energy is the energy by virtue of pressure. Kinetic energy is the energy by virtue of motion. Potential energy by the virtue of its position, and it remains constant along the streamline. Along that particular streamline, it will be remains constant at particular section. This is the Bernoulli's effect. That the constant energy at particular section, what we are going to take, that is called as a Bernoulli's effect. The Bernoulli's equation can be written as the sum of all the three energies: the pressure energy, kinetic energy, and potential energy, that is equal to constant. Where this, what are the terms we have taken? The P is pressure energy per unit volume in Pascal. Rho is density of the fluid in kg per meter cube. V is velocity of the fluid in meter per second. G is acceleration due to gravity in meter per second square. H is height above the reference point meter. That is, H is height above the reference point. That is also called as elevation. And this equation shows the relation of pressure, velocity, and elevation of a fluid, and how the Bernoulli's equation in fluid mechanics helps in building this relation. Now, taking a sketch to derive that Bernoulli's equation, at two sections we are going to consider: a section 1, and where the area A1 is there and velocity V1, and that distance of that section we are going to take the small distance dx1, and where the force is acting as F1, and that is equal to P1, pressure P1, and area, cross sectional area A1, and dV, whatever the volume, small volume of the fluid at section 1 we have taken as a dV. Then at section 2, okay, that is at a elevation of the y2, and this is at a elevation y1 section 1, and which is having the cross sectional area A2 and its small distance dx2 and velocity v2, and its volume flow will be dv, and where the force is acting F2 is equal to P2 into A2. And by considering these two sections, if you write the work done equation for this, according to the Bernoulli's theorem, the work done by fluid can be written as the work done, small amount of work done at each section can be taken as dW is equal to F1 dx1 minus of F2 dx2. Then that can be written as the F1 is a P1A1 dx1, and F2 is the P2A2 dx2. Then dW can be written as here the P1 and this A1 and dx1 will be the dV, the smaller volume of that fluid cross section what we have considered. And here also the A2 dx2 is the cross sectional area multiplied with that distance will gives the again dV. And this can be written as, okay, the dV is taken common, P1 minus P2 into dV. As known, the work done on the fluid was due to the conservation of change in gravitational potential energy and change in kinetic energy. The change in the fluid's kinetic energy is given by dk, that is a change in kinetic energy from the section 1 to the section 2 will be half m2 v2 square minus of half m1 v1 square. And this is the kinetic energy at section 2 and this is kinetic energy at section 1. And that can be written as half, and this mass whatever is there, that will be remain same at section 1 and section 2, the because of the conservation of mass. That can be written as mass can be written as density multiplied with the volume. That will be mass density in kg per meter cube, and this volume will in meter cube. Then we are going to get as a mass in kg. And this inside what will have the velocity difference, velocity square difference is v2 square minus of v1 square. Then change in potential energy can be written as du is change in potential energy, that can be given as mass multiplied with the acceleration due to gravity and elevation at section 2 minus of mass at section 1 and acceleration due to gravity and elevation at section 2. And here again, this mass can be written as rho into dv. Okay, the rho into dv that can be written as, and that can be taken in common from the both the terms. Then we can write rho g dv y2 minus y1 as a change in potential energy. Now, according to the theorem, the energy of the system is same as the summation of the change in kinetic energy and the change in potential energy. This can be mathematically written as dw is equal to the work done equal to change in kinetic energy and change in potential energy. Substituting the values from the above equations, that is P1 minus P2 into dV is a dW, and dk is half rho dV V2 square minus of V1 square plus of du equal to rho g dV into Y2 minus Y1. Now the dV will be get cancels from all these three terms, and equation can be written as P1 minus P2 equal to half rho V2 square minus of V1 square plus of rho g Y2 minus Y1. Here, by rearranging the above equation, we will get the Bernoulli's equation as this P1 will take, will write as it is. Then from this whatever the V1 is there, half rho V1 square. Okay, half rho V1 square we can take plus of from this rho G Y1 we can take this side. We can write the one equation at section 1. Similarly, this P2 can be sent to the right hand side where we can write this P2 plus of half V2 square and plus of rho g y2. That half v2 square will be this side only, and this will be half v2 square, and rho g v2 will be remains on the right hand side. Therefore, this equation we are going to get. From this equation, we can see the summation of pressure energy, kinetic energy, and potential energy at section 1 is equal to the summation of pressure energy, kinetic energy plus of potential energy at section 2. Therefore, the total energy of this summation of all the three forms of energy, that is a total mechanical energy, will be equal to constant, which is the Bernoulli's theorem or a Bernoulli's equation. That is P plus half rho V plus of rho V square plus of rho G y. Here this is a square, rho V square plus of rho G y is equal to constant. This is commonly we can write the pressure energy, kinetic energy plus a potential energy equal to constant if you apply at any section. And that equation what we are going to obtain, that is called as a Bernoulli's equation. And this equation will be applied for the different fluid flow, and those applications I am going to discuss in the next session. And also the Bernoulli's equation derivation from the Euler's equation also I am going to take in the separate session. Thanks for watching. If you like, share, subscribe and comment.